I'm just going to give a quick disclaimer. So this presentation is aimed at people like you. It's aimed at you guys, people with no physics knowledge. So like, don't be put off. Don't just like turn off and be like, oh, I'm not listening. I don't understand physics. It's a Christmas lecture, which is something the BBC does, where like every year, I think it's Institute of Physics, they do what's called a Christmas lecture, and they get like loads of kids in, and just like the general public, and it's someone of like scientific field, and they just give a talk about their science that they do, but so the general public can understand it. So if you've been in this channel for a while, you probably know that I have a physics degree and I'm also a photographer. So I did a little bit about black holes in uni. I mean, my dissertation was more on about like galaxy clusters, so nothing to do with black holes. But I did learn all of this stuff in uni, and I thought, you know, it'd be really cool, pictures and physics. So that's what I'm doing. But I am going to start off with a tiny bit of science. So these are just like the key things that you need to know if you don't know anything about physics. So I have put it up on the screen here, and I will keep it on for like any pages that needs it. So the number one fact you need to remember is nothing can travel faster than the speed of light, and we write that as c. So c is just the speed that light travels. And then 2, so light can behave as a wave and as a particle, but for this presentation, treating them like with black holes and stuff, we will treat light as a particle. So I've just written here, light is a particle. And then the third one is this little Einstein equation, E equals mc squared. So you don't need to like remember the equation or use the equation. Basically, that equation just says that energy can be turned into mass and mass can be turned into energy, basically. So energy cannot be created or destroyed, only transformed from one form to another. For example, into mass, which is where E equals mc squared comes into. So there are 2 parts of this. The first part of the presentation is what is a black hole? And then the second part of the presentation is taking pictures of black holes. So the physics definition is a region of space having a gravitational field so intense that no matter or radiation can escape, which basically just means it's so big and heavy and dense that even light can't escape the gravitational pull. I will quickly explain how black holes are formed. Not that it matters for taking the pictures, I just think it's quite interesting and maybe people didn't know about this. So you start off with this stellar cloud, which is just space. It's got gas in it, and then the gas will like condense down and form what is called a protostar, which is basically just like an early baby star. And then stars go on to something called the main sequence. And then this diagram here, we've got small star. So that is a star like our sun. You might think our star's quite big, but it's actually not, it's quite a small one. So when that uses up all of its fuel, it will start to expand and become what's called a red giant. And then eventually the outer layers of that will explode off. And then the core that's left behind will condense into what's called a white dwarf, which is a type of dim star. Whereas large stars, they go into a red giant and then a supernova, which you've probably seen like loads of pretty pictures of these on the internet. But for stars that are bigger than 25 of our suns, they will condense into a black hole. So a black hole is like loads of matter condensed into such a small region of space that the gravity is so heavy that like nothing can get out of its gravity. I've also put in this as a visual aid. This is a computer generated image. This is not a picture of an actual black hole. This is like computer generated. But this just gets the picture in your head of like what a black hole would look like. And again, you don't need to remember the terms. It's just for those who do want to know a little bit more of the science, I've put them in here. So the actual black bit here, that's called the singularity, and that is the black hole. And then I will talk more about this in a bit, But this edge here, when it stops being black, this is the event horizon. So I will touch on that in a little bit. It's just for you to know, that's when I'm talking about event horizon, that's what I'm talking about. And then the outer area is the accretion disk. There are more features, but these are the key ones that we're going to be talking about. So now a little bit of history, which I found really interesting. So black holes, you know, people have been talking about them pretty recently. Spoilers, the first picture of a black hole was actually in 2019, and then we took a picture of a different one in 2022. So it's very recent physics. But they were first theorized in 1783. So I've just written a bit here that it was theorized, now known to be true, that a light behaved as a particle, which must escape the gravity of what it emits. So if light is a particle, the star emits this particle, and you have to escape the gravity of the star for it to get all the way to us. So gravity is stronger for more dense objects, which is why on the moon you can jump a lot higher than on the Earth, because the gravity of the moon is a lot less, because the moon is a lot less dense, it's a lot less heavy, so the gravity isn't as strong. So it was theorized that if the density of an object was large enough, the speed at which something must propel itself away from the body that is emitting the light must to escape the gravity, could be the speed of light. And if it was the speed of light, then it's never going to escape, because as we remember, nothing can travel faster than the speed of light. So at this density, the star would be a dark star, which is actually a better way to describe it than a black hole, because essentially it's emitting light, but it's just like, it's taking it back. This turns out to be true. And once objects get closer to what is called the event horizon of the black hole, they are sucked into the black hole, never to return. So this was in 1783, but shortly forgotten because it was found out that light behaves as a wave. So they're like, well, if it behaves as a wave, this can't be true. We now know that it can behave as a wave and a particle. But with this idea of if an object was condensed enough, it could be a black hole, you can imagine that this could happen to any object, which is true, right? If you took the Earth and you took all of the mass in the Earth, all the people, everything, and you condensed all of that mass into a space about the size of a pea, that would be a black hole. Obviously, that's not going to happen naturally, but just say that you could do that, that would be a black hole. So in 1915, Einstein came up with his general theory of relativity, which I won't get into because that's like degree level and above. But basically, Einstein made these equations, and the solutions to these equations described a simple black hole. So finally, people were talking about black holes again. So in 1967, the term black hole was coined by a guy called John Wheeler, which is somewhat of a misnomer because it's not a hole. You're not filling anything. You're just adding mass to it. But the name stuck, so yeah, they're black holes. And then throughout the 60s and beyond, we found a lot of evidence suggesting that black holes did exist. And one of the most promising pieces of evidence was stars orbiting around seemingly nothing. Just how we orbit our sun, like the Earth orbits around the sun because the sun has a lot of gravity. The stars within our galaxy, the sun, is orbiting around a black hole in the center of the galaxy. So I'll just show you this video. I was so scared it wasn't going to play. But these are like the paths of some stars. They're called S stars. And as you can see, they are all they've got different orbits, but they all seem to be orbiting around this one central point. So that's a clue that there is something there that we need to go and look at. In 1974, Stephen Hawking said that black holes radiate energy. So this is probably one of the most complicated bits of science I'm going to go through, but just bear with me. Stephen Hawking said that black holes can actually radiate a small amount of energy in the form of thermal energy. So in the space just around the black hole, you can create particle-antiparticle pairs because of E equals mc squared, so the energy can be converted into mass. One of the particles falls into the black hole, and then the other particle escapes, and that gives off a small amount of thermal radiation. Now, because it's so small, we haven't been able to detect that, but that gave us the idea of looking around the black hole rather than actually imaging the black hole directly. In 2015, we discovered gravitational waves, which isn't really anything to do with picturing black waves, but it's evidence that they exist. It's very complicated, but still interesting science. And this is a little diagram of two black holes rotating around each other. Those waves are gravitational waves. And at some point, they collide and they release a shock wave. Now, gravitational waves, they do not get absorbed by things because they're not normal types of waves. So we detect those waves, which just shows us, oh, there's some black holes there. And then we know where to look. And then in 2019 was the first image of the black hole. I was literally in my second year of uni, and I remember my lecturer at the time, he cancelled his lecture and he did a talk on this image instead. And it was like such a huge discovery that it's estimated that over 3 billion people saw this image, which I think is really cool. So now we are finally talking about taking pictures. So what do we actually see in here? This is a bit sciencey, so if you don't get it, it's whatever, it's fine. So around the edge of a black hole, you have electrons, and those electrons, they're spinning around like on their axis, so they're going around the black hole, but they're also like spinning like that really, really fast. So if you don't know what electrons are, they're charged particles, by the way. So the magnetic field causes them to spin really fast. And that spinning causes them to emit radiation called synchrotron radiation, which is not important to remember that name, but I just thought people might be interested. And that gives off radio waves. So essentially, we are looking at the radio waves created by the electrons around the outside of the black hole. So we need a radio telescope to see them. So what does this image tell us? The center dot here, this is the black hole, and this tells us the size and the mass of the black hole. And then you see around here, we've got the bright spot and, well, the bright side and the dim side. This tells us that the black hole is spinning, and it tells us that it's spinning towards us. The bigger the difference in brightness tells us how fast it's spinning. Sorry, my cat's just coming to sit on my keyboard. So this side is spinning towards us. This is about like Doppler shift, which I'm not going to go into that, but essentially bright coming towards us, dim going away from us. So what telescope do we need to picture a black hole? So black holes are very, very far away, and the closest one to us is in the center of our galaxy, and that is called Sagittarius A. But it's actually relatively small compared to other black holes, and it's hidden by the rest of our galaxy. So if you picture this as our galaxy, because galaxies are flat, in the middle is our black hole, and on the edge is us. We have to see through all of those stars to see the black hole in the middle. So what did we do instead? We looked at, I think it's called Andromeda Galaxy, which is a bit further away, but their center black hole, M87, is huge. Now, taking a picture of M87 from Earth is the equivalent of taking a picture of an orange on the surface of the moon. So we need really high resolution. And like I said earlier, we need radio waves. So you may know that there's the Hubble Space Telescope in space. That's in space because it takes pictures in a wavelength that's absorbed by our atmosphere. Luckily, radio waves aren't absorbed by our atmosphere very much, so we can use land-based telescopes. So there are maths equations behind it, but I'll just summarize it in saying the bigger the lens, the better detail you have. So that's why your garden telescope and the observatory telescope, they can both take pictures of Jupiter, but this is going to be like in a lot more detail because the lens is so much bigger. So it's got higher resolution because the lens is bigger. Now, if we've got our constraints of radio waves and the resolution we need, the issue here is that the telescope would have to be 10,000 kilometers diameter. Now, the Earth is only 12,000 kilometers in diameter, so this is literally what the telescope would look like, which isn't possible. So instead, we take many radio telescopes from across the whole globe and virtually link them together. Each telescope takes a little bit of the image, and then the images are stacked on top of each other to make a complete picture. This is called the Event Horizon Telescope, and this is what was used to take the famous picture of M87. So here's a little video of how they do it. So you've got each one of them dots is a telescope, and it's rotating because the Earth is rotating. So the ones far away, they have clearer images, and then the closer ones a little bit more blurred, and then it stacks on together and you have the overall image. Now, what was really cool about this is when they simulated it, they got something that looked like this. Now, if you blur that, because even though our resolution is really high, it's still not perfect, you get what they observed. Now, when we did the same thing for Sagittarius A star, which is the black hole in the center of our galaxy, it wasn't as good. So you see how there's like the bright spot, the bright spot, the bright spot. That shouldn't happen because that's essentially saying this side, and this side are all coming towards us, and this side, and this side are all going away from us, which obviously can't happen. There's just a lot of error within these stacked images. And that's because, have I written why? Yes. So first of all, it's hidden by more stuff. So it's harder to get accurate pictures. Now it's closer, but it's smaller. And because it's smaller, it spins a lot quicker. So whereas this one here, M87, it rotates on, I think its orbit is like 2 weeks. So from morning to night, it looks about the same. The orbit of Sagittarius A star is 4 minutes. So it will look different from 1 minute to another, which is why the images stacked look a bit messy. So the Event Horizon Telescope project is still ongoing, and they plan to refine the wavelength used to provide us with better imagery and even videos of black holes, which is pretty cool. And that brings me to the end of my presentation. And then I'm going to look back at chat again now, guys. Oh, so sweaty. Hi, welcome back. How y'all doing? I feel like I was getting so nervous there at the end. And I was like,